Okay, Maria, do you want to bring up the presentation then, and we can?
Taco needs to add the presentation to the stream.
Okay, right. Okay.
Hello.
So
Hello.
sorry, we are having some technical difficulties, but this is going to be starting very soon.
This one.
Yes.
Excellent.
Perfect. Thank you. So hi, everyone. We are finally here. Thank you, Taco.
Shall we introduce ourselves then, Maria?
I guess so. So hi, I'm Maria. I'm Java champion. I'm a software engineer working for IBM on the OpenJDK team. And this is Andrew. Andrew, you can present yourself.
I'm also in the IBM, formerly Red Hat OpenJDK team, working on the JVM. And we're both involved in the Leyden project, which is what we're talking about here today. So should we move on to the next slide?
Yes. So Leyden project, what it is. Maybe you have heard of it, maybe not. It depends on how close you follow latest Java news. But this is a project that was announced or started on May 2022. And the idea is, well, it has had a very slow start, 2.5 years of development already. And it tries to focus on startup, warm-up times, and eventually footprint. That's the part we haven't tackled yet much. We have already 4 deliverables since JDK 24. First, it was around class loading and linking, then trying to make this more easy to use with the command line ergonomics, then adding some method profiling. We will see later what this all means. And for JDK 27, we are working on caching some code already, which is going to be, we are going to show how a big difference with JDK 26. We are going to discuss about 26 and 27. I know 26 is not yet a release, but the code is frozen, so you can already start testing it, using it, and it's going to be very close to what the final JDK release is going to be. And as it says there, this is a multi-vendor project, so this is not something that just Oracle is doing or just a couple of crazy developers is trying to do. This is a big effort made by, why? It's gone. This is a big effort made by several big companies. And anyone that wants to join this effort is really welcome, because one thing that we value here is that people, after this talk or after reading a bit more about Leyden, maybe people want to test this and share their results and share what they think about this.
Yeah, I'll just add to that before we move on, Maria. This is a very large ticket project. There's quite a few big projects, and many of them have delivered things as a great slab after a lot of work, or in several big pieces over a long time. And one of the things that's been followed with this project is that we are actually delivering things incrementally, because as a performance improvement project, we can start improving performance right away with individual pieces. That's why we've delivered 4 pieces so far over the last 3 JDKs, and we're delivering another big piece in the next JDK. And the project will be continued to doing incremental deliverables. So we're hoping to give people the opportunity to get gradually better and better performance. In particular, we've got stuff in for the LTS release in 25. And the core things to do with improving startup and warm-up, we hope to get in and have them really well tuned and usable in JDK 29. So we should get big advantages out there for you to use in your deployments, either for the development cycle or for the long-term support cycle. But we see this carrying on to do more work on startup and warm-up, and also in footprint into JDK 33 LTS release as well. So over 29, 30, 31, 32, we'll be adding more capabilities to improve the performance.
So let's get into the details. As you very well know, Java is a very dynamic language which means that it supports a lot of features like being able to be transformed or changed during runtime. And this is something that is a feature that can be used on a way that helps reaching a peak performance that is really good. I'm not explaining myself right. Let's see this with the graph. So when you start a Java application, it starts very cold. You have your jar file, which has bytecode classes, and it has some meta-inf information, some resources. And the first thing that your Java application has to do is start by setting up the JVM, the JDK and the JVM, and start loading some classes related to the JVM, and then link them, maybe compile them, run them, and then you start reading the classes from the bytecode, the classes that are from your application, and then it starts loading them into a model in memory that is the metadata model of classes, methods, and how the hierarchy of classes describes your application. And then you link those classes, you start compiling, or you start first transpiling to native code, and then your application starts running. The moment your application starts running and starts delivering some responses, for example, if it's an API, or starts really running your code, this is what we can call the startup time. And then at that startup time, the application is still a bit cold because all your code is on bytecode. Whenever you need to load a new class, you have to read it from bytecode, transform it to this metadata in memory, and then you need to maybe link it to other classes, check this field corresponds to this other class, so I have to maybe load another class while loading my first class. So there's a lot of startup things that needs to be run before your application really starts running. And this is why running a Java application is not instantaneous in theory. And then once it starts running, it starts getting some profiling data on how the methods run, like it checks which methods are the ones most used, which ones are hotter, which ones are, when the method runs, it checks which branches are used more or less. It starts getting some profiling data. And after some time, it starts recompiling this code you're running from your application and from the JDK. Using this information on profiling and also your hardware specs. So it starts compiling with some optimizations and some optimizations that make it run faster and faster. This is what we can call the warm-up. At some point, it's already warmed up, and then it runs faster and faster. And it reached some peak performance that is really fast. Everything is compiled using this profiling information. Everything is very well optimized, more optimized than any code that you can build to native statically on build time, because you have information on how your users are using your application or how you are using your application. It has information on exactly what hardware you're using, so it can use a certain set of instructions on native that are making the code more optimized. And then it's really fast. So what if we could start this application already warmed up? And that could mean that instead of having to wait for the startup time, loading all this metadata from the classes and compiling the code and starting to profile, what if we had all this information already at startup? Then it means we could start on peak performance. So this is what Project Leyden is trying to do. It tries to get this information on the IoT cache. Maybe Andrew wants to explain this part.
Yeah, so the idea is that we do all this work to get the JDK runtime prepared and running tuned, highly tuned compiled code, get the application to start working and to have really highly tuned code. And what you find is that certainly for the JDK runtime, every time you start up, it does almost exactly the same thing every time if you're deploying to the same machine. Generates almost exactly the same compiled methods with the same hot paths, ignores the same cold paths that normally don't get executed. So all this flexibility we have, we actually end up repeating work that we could maybe reuse to get to exactly the same point. And we built up information inside the VM, a model of the code base, connections between classes so that when we make a method call, we know exactly where the target method is. When we access a field, we know where the data is. All this stuff we've got, all the compiled code we've got, all the profile information about how the thing ran last time and therefore how we should optimize or re-optimize if we recompile. That's always going to be repeated work. So if we sort of short-circuited and took all that state that the VM has built up internally, all that metadata, objects we've created, classes we've initialized, code that we've compiled, and stuck it on disk somewhere in a state where we could just suck it straight back in the same format that the VM has created it in, we could bypass all that work. Now, the problem is that if you run on one run, sometimes when you run the second one, it's not exactly the same. So we're relying on the fact that most of this stuff will be the same on any different run, and we can reuse it. And if we can find a way of quickly dumping this information from when we're running in a hot VM and then sucking it back in really quickly, we'll bypass all that work we have to do, and we'll be running hot very, very quickly, because pulling it in should be a lot slower than creating it bit by bit from the bytecode, from running and finding out how it operates in a particular run. So what we've got in the Leyden model is we have a training run where you run the application to train the JVM, and the JVM in executing the code builds up all this state. And then at the end of the training run, it builds a cache that dumps what's in the VM in a state where it can actually reload it. As long as your classes are the same classes, or maybe they've got a few extra classes, but as long as you've got basically the same class path plus a few extras, when you rerun in your production run, all the stuff that's in the cache should all be valid and usable, and should avoid you having to do a whole lot of work to get to that hot state. You can just pull it in and reuse it, pull code in when you need it, pull in a pre-processed metadata class that means you don't have to actually work through all the bytecode and decode it all and understand what the class looks like. The JVM knows already what the classes look like. It knows how they cross-reference each other and so on. So that's the model for this. And the critical thing for getting this to work well is that your training run actually looks like a production run. If you can do a production run where you monitor behavior and then dump from an actual live deployment, that would be the sort of perfect case. If you can run something that looks a bit like a live deployment, say a sandbox deployment, where you're using synthetic data, say server requests from a driver of some sort, that'll give you something that's close to the actual production run. So the key thing that makes this work is that you actually train your application in a way that looks like what's going to happen in the real deployment. And the nearer you can get to that, the closer you can get to having everything you want and just grabbing it as you need it during startup and get rid of all those startup overheads. That's the model that Leyden has. Okay, next slide, maybe.
So what is exactly inside the cache? What kind of things we are storing? Because what we cannot just take the memory we have and dump it and then load it again. That won't happen. That doesn't work. So
that's because the memory addresses are randomized, so you can't just pull it back in exactly the same place. There's a little bit of massaging to get the data that was in the right format out to a cache in disk and then back into the VM. Go on, Maria.
And also because loading directly on the memory without checking anything is a bit dangerous, yeah. Let's say. So what's inside the cache? I have talked before about the metadata. When you load a class to memory to use it, you generate this metadata, this hierarchy of classes, these methods, and this is part of what is inside the cache. There is, you can see here, there is a part that is static, there is a part that is dynamic. You may think that you have heard about this before, and it's true. We have the CDS, this system that has been since, I don't remember, with JDK for a long time.
JDK 13.
13. So since forever, where we already loaded part of the metadata from the JDK, not from your application, but from the JDK. You loaded it directly on memory because for each JDK, you have the same classes. I mean, Javalang class is always the same. Javalang string is always the same. You already know what is going to be the result when you load them into memory into this metadata hierarchy. So, well, metadata tree, set of classes, it's not a hierarchy exactly. But you know exactly how it's going to look on memory. So you can load it directly. You don't need to process it and then load it. And that's the idea. But now we also include your classes from your application. So the classes, the methods, the constant pool, all these things go directly. You generate during the training run. You generate the metadata model, and then you can load it directly into the cache and then into memory. So the classes, the methods, that's pretty obvious. This comes directly from the source code. The constant pool and the constant pool is part of what allows linking classes. Also, type arrays is very similar to a class, but related to an array of certain objects or primitive. And then you have symbol annotations. This is part of things that you can derive from the source code directly. So this is part of things that you could generate during build time. This is directly derived either from your source code or the JDK. And this is basically you build the metadata model. I would say that this is the summary of what the static part is.
There's one other thing. You also have some heap data because bytecode has references to string text in the bytecode. And when you load a class, you create strings on the heap, that a unique string that represents that text as Java objects. So we put some Java objects into the archive and repopulate them in the heap as well, because the metadata needs those strings to exist. When a class is loaded, the strings that the methods refer to as constants have to be in the runtime. So they're also in the archive. So it's not just the model of the class base that's in there. There's also some Java objects that we pull in. And we'll come on then to the dynamic data, which follows on from that, because there's more objects. But let's talk first about, so as well as that stuff that's the fixed model of what the class base is, that is the same every time, that model is sort of gets added to with extra information by virtue of running methods. When you run a method, during your training run, this will be, or during a normal run, you keep track of how many times that method is called. So there's a method counters object, which is hung off the method. That's a dynamic thing. It's only created during execution, when the JVM is running, but it's some JVM state that's added to the class model. And if you run a method enough and you start looking at how it's executing in more detail, you might generate some C1 code, the base compiler, and actually profile it and get information about which are the hot branches, which are the cold branches. So you keep, and sometimes you can do that also from the interpreter, keep track of some of the branch statistics. You keep track of argument types, things like that. So you can actually get detailed information in the execution of a method, and that's stored in a metadated object. That's another thing created at runtime and hung off the methods that are in the class model in the JVM. So this is beyond what's in the bytecode. It's not just something that's translated off the bytecode. It's runtime information that's hung off it. Now, the third thing is a thing called a constant pool cache, and it's got a rather unusual name. What it actually is, it's a linkage cache. When you come to execute a method, you have to know which target method to call. Now, in the bytecode, it says call method foo of class foobar or some whatever name. You've just got names in the bytecode. When you build your class model, you've got the method and you're going to execute bytecode or try and execute it compiled. You know that you've got to find a class called foobar and you've got to find a method called foo, but you don't even know whether that exists yet. So the first time you make a call at some call site, you've got to work out what's the actual target class. Does it exist? Maybe I need to load it. If it is loaded, does it have a method called foo? Does the signature match the arguments I'm about to pass to it? And you could get a linkage error at that point. It doesn't normally happen, but it is possible to get actual system errors because you've got the wrong bytecode classes in place. But you've got to work out where's the target of that method, and then you find a method that's in your class model and you link it directly to the calling point from the calling method, so that next time you call that method, you just find the target and either execute it bytecode in the interpreter, or you jump to its compiled method. If it's a compiled method, you jump straight into the target address for the compiled code. And similarly, when you access a field, if it's a static field, you need to know where the class's data is stored, the static field data. If it's an instance, you've got an object, you need to know where in the object does this field sit. So first time you try and access a field called my data or my address, you actually have to see if the class really does have a field called my address and work out if it's static or instance and work out where it is. And then every other lookup from then onwards knows exactly how far to offset into the object, exactly where to look in memory. So this constant pool cache is actually where we store the linkage information. And that linkage information, if it's established on a training run, can be reused. You don't have to stop, go and search through the code base and work out where to call the method, where to look up the data. You just do it directly first time. So this is an overhead that we can avoid by keeping both the profiling information and the linkage information in the class, the cache. We can avoid having to do that when we rerun the application in the production run. It's already there available for us. Now, the third thing we can do is also we can initialize classes. This is only done in a limited way at the moment. It's the thing that GraalVM also does. So one of the things that you can have in your Java heap is a Java-lang class object. And now, not everybody knows this is actually how it works, but in the Java-lang class objects in the heap is some space where you store the static field data. And that Java-lang class object that represents the class in the Java world is only created when you run a class initializer. When you first load a method and try to use it, there's a lot of static code, a lot of static field initialization that gets run. So if you have a Java-lang class object in your heap, that's because you've initialized that class, and you only do that one-off. Now, we can do some amount of that initialization during the training run. We can store the values of the static fields in the class object, and then we can save that class object into our archive and pull it back into the heap and avoid having to do class initialization, avoid having to run all that in it. And we can pull in all the objects that the static fields refer to, or if they're just numerical values or primitives, we pull it in with those primitive values in place. So as well as having strings in the heap, we also have Java classes as the Java lang class objects in the heap, and having those avoids having to run class initializers. So doing this work, all this method profiling, linking of classes, creating heap objects, and particularly class initialization for class objects, can all be done by saving that dynamic data that got created during the training run and then pulling it back in. We can't do it with everything. It's a limited capability for the class initialization at the moment, but we're working on adding more and more class initialization. And this saves us an enormous amount of work in the production run.
Maybe we can talk now about training data, profiling data.
Yeah.
So part of what gets stored in the cache is the training data, the profile data that helps later compile with better optimizations. So this is what you can see up here: class training data, method training data, compile training data. Usually these classes don't have much information by themselves, but they are the ones that link, for example, all this information we said about the branching, which methods are hotter, which methods are more used, which branches, how it gets used. And the idea is that, class training data obviously is associated to a class, method training data is associated to a method, and compile training data is also associated to methods. And I don't know if you already know that Java has different types of compilation. So depending on how hot a method is, it tries to compile with higher optimization. So you can have more than one compile training data per method, depending on the different levels of compilation. So you can have information for compilation for tier 2, tier 3, tier 4. And this is mostly what it is. This kind of data is already in JDK 25. Maybe not all of it, but at least class training data, method training data, I know it is there. Compile training data, I'm not so sure, but
yeah, the compile training data is there to keep track of method profiles, which are saved in JDK 26. So they exist but to keep track of the method data and the method counters. These training data objects sort of form an index for what's in the rest of the metadata, because the rest of it is laid out in JVM format, the way that the JVM expects. This stuff sort of provides you an access point into that. So when we build up that index when we're training, and when we're in production, we can use that index to access things and pull them into the JVM as we need them. So that's our sort of entry point. It's more, these objects really form a sort of global index for things. And then the final thing we've got that adds to that is in JDK 26, we haven't saved compiled code. We're not able to restore compiled code. We do save method data and method counters. So we know about how a method ran, and that means we're able to compile it quicker because we already know what's the hot paths, which things to optimize. But we don't actually have to compile code. In the prototype that's in the Leyden repo, and what we're working to get into JDK 27, we actually save compiled code. So that splits into two halves. There's compiled code that's used. We actually generate machine code inside the VM to do things like unwind the stack, or to deal with a bailout when we hit a cold path and decide, which we didn't decide to compile. We have to decompile a method and then re-enter the interpreter. There's all sorts of management methods that are created that link together bits of code that we've actually generated from Java or get called out to from the interpreter. And so and there's also bits of code that do operations like computing a sine or a cosine, optimize little kernel routines that it's better to generate with handcrafted code rather than to do by compiling bytecode, because you've got better performance with handcrafted stuff. So these stubs and these adapters are things that we use to glue all the code together and glue the interpreter into compiled code. And we generate them during startup. We might as well save them and restore them. So there's the ability to save and restore adapters and stubs already in the pre-main implementation. Adapters are actually being saved in JDK 26. There's a limited amount of that. But the really big ticket thing, which we're getting for JDK 27, is if we compile a Java method, we can save that compiled code and reuse it. If we compile it with the basic compiler, the C1 compiler, we can save it as a sort of simple method. We can save it with profiling instrumentation code in there to record statistics if we want to be able to run it and get better profiling in the production run, or we can save a fully optimized version. And that's one of the things we try to do most of all. We try to save fully optimized methods as much as possible, because if we've got code that during the training run that was really hot, it's probably going to be really useful to us during the production run. So we've got the ability to store compile code into the cache and pull it back in when we come to runtime to production time, and get all the benefit of having code straight away without having to wait to profile in the interpreter, without having to run a compilation. We just dive straight into compile code. Okay.
Let's move to some examples, I think.
Yeah.
So we have been running some testing to see if this works. And we are going to show, this is a pretty easy application. This is a REST API using Quarkus that calls a Postgres database. This just have some simple endpoint that creates a select query that does a lookup on the database and returns the result. And we are using the OHA driver to generate a lot of requests. We are using request rate that is fixed, so we send the same amount of requests to all the different versions, and we are using here 4 cores. How many cores we assign to the applications, 4 cores or 2 cores. We are using JDK 26, and we are using pre-main, which is this JEP that we are going to deliver in JDK 27, we hope. I expect it to be in JDK 27, that we have been talking about, that is also storing the code. It's not only storing metadata and profiling, but it's also storing the code compiled. And we are going to compare also different versions of the Quarkus, because Quarkus right now, as you can use it, it has a very well custom class loader. It's a dedicated class loader that saves a lot of time when looking for classes and resources. And it allows for a non-flat class path. But that poses a problem with Leyden right now, because Leyden does not work well with custom class loaders at this point. So we are comparing it to the Quarkus version that does not use that class loader, which is the Quarkus UberJar. And maybe Andrew wants to talk about this and exactly what it means.
I'll explain a little bit of the application. We're using a fixed rate because we want to compare apples with apples. We want to drive the server with a fixed number of requests, and we've loaded it about 2/3 of its peak capability. So it's not running at absolutely full belt. It's got a little bit of slack, but it's running at a fairly high rate. And we keep that constant where we have the AOT capability enabled or the AOT capability disabled. And so without AOT, we'll see what the baseline performance is for either JDK 26 or Premium. They should be the same because they're roughly the same JVM. It's just one's got the code saving capability in. But we also run it with AOT. And what we can see is what benefit we get from running with the cache providing stuff that we need rather than having to build stuff as we go along. Now, there's two things that we can measure. We want to measure how quickly does the application get started. So we can identify when the port gets opened, the 8080 port, and that's our measure of the application started. We've got into main, we've opened the port. The application's done a little bit of work. It's actually run the Quarkus framework code and a little bit of stuff to open a port, set up Netty maybe, but we're basically at the start of that point. What we're also then going to do, we take the requests that happen over the first 10,000 requests, and we see how long each request takes. And this is called a jitter test. If a request takes the time that we take at about peak time, which it turns out to be about 0.1, 0.2 milliseconds, then that request wasn't interrupted by anything. If the request takes longer, that means the JVM is doing stuff and interfering with the server. So the request profile, how long requests take as we go along, and how long they take to quiesce to get to the point where they're taking a uniform amount of time, gives us an idea of whether we're warmed up or not. If we're seeing a lot of interference, we're still in warm up. Once the request timing stabilize, we're warmed up. So that's what we're going to use to measure how this application works. So we're going to talk through the Quarkus and the Quarkus UberJar cases without AOT now, and then we'll look at what AOT gives us. So
yeah, so the Quarkus one, you can see that of course doing without AOT is very similar. The version UberJar is a bit slower, as I said, because it has it doesn't have the dedicated class loader, but it's almost the same. The thing is, maybe we can. Yeah, so the thing is, even if it's slower, the UberJar, because it doesn't have this dedicated class loader. I don't know why you don't want to add the AOT to the conversation yet, because I think this is the moment.
Well, the first thing to mention is that it doesn't matter whether you've got 2 cores or 4 cores. It doesn't make any difference to the startup, because most of the startup is single threaded. So the number of cores you have available doesn't really influence things very much. But yeah, when we look at what the AOT does, there's essentially the UberJar is just slightly less performant than a normal jar because it doesn't have an optimized class loading, but all the classes are in the class path. That's the important thing. So with the Quarkus jar, there's only a subset of the code that we can actually put into the cache. We can only cache a certain subset of the classes. We can only cache the methods for those classes. We can only cache the linkage for those classes. If we have a call that links through to one of the dedicated things that are loaded by the Quarkus loader, that linkage information has to be scrubbed because we don't own the classes that are loaded by the Quarkus loader. It's not safe to rely upon them being the same even. Until we get support for custom loaders integrated, we have a limited set of classes that are available. So what you see when you look at the AOT being mixed into the Quarkus loader, say for the 4-core case on JDK 26, there's a big improvement in the startup time. We get to open the port quicker. That's because instead of creating a whole load of stuff, we end up actually using assets from the cache, and pulling them from the cache is way, way quicker than creating them. So we get quite a big percentage, about a sort of 30 to 40% improvement there. If we have compiled code, if we have the UberJar, there's far more classes in our cache when we have the Uber jar. So we're getting more benefit because instead of having to actually load bytecode, compile methods for those, link classes for that situation, we do linkage in JDK 26, compile stuff with existing profiles for just a subset of the classes. We can now actually get classes loaded, pre-linked, and have method profiles for most of the classes in the runtime. Most of the classes the application needs that are normally loaded by the application loader. So we get a much bigger improvement. And although we started off maybe 100 milliseconds slower, we actually end up getting a much bigger improvement. So that's the situation with pre-main where we haven't got compiled code. When we actually can have compiled code in the cache, we get an even bigger improvement. With the JDK 26, there's no seeing code. With the pre-main prototype that's in the Leyden repo, we get an even bigger performance increase. We've got about getting on for 60%, and for this case, even if you allow for the penalty and you started from where the normal Quarkus case was, we're about 70%, or actually 80% for the UberJar code ahead with this version. So we've really got an enormous improvement from having the extra compiled code as well. Now that happens when you've got 4 caches. Why is the improvement not quite so good when you've got 2 caches? Two processors, sorry, 2 cores. So we still get a big improvement in both cases, and the improvement is bigger for the Uber jar than it is for the normal jar, and it's actually still slightly bigger for the case where we have compiled code than where we don't have compiled code, but it's not quite as much. Now, why is that? Well, when you've got 2 cores, in both cases here, we're still doing a certain amount of work loading the classes in from the archive rather than from bytecode. We're still doing a certain amount of linking that we have to do because not everything's linked. With JDK 26, we still have to do a bit of compiling because we don't have compiled code. We have method profiles. We can start compiling earlier, but we still have to do compilation. So there's still some overheads of the JVM doing background work, and those overheads are stealing cycles from the application. So with 2 cores, they steal more cycles relative to the amount of work the application does. This one we have 6,000 requests a second. This one we have 3,000. So that's the server's being loaded at the same rate, but the amount that the JVM is stealing time from the application is greater when there's 2 cores because it's got the same amount of work to do. So you notice you don't get quite as good a benefit on a really low CPU count deployment as you do on a slightly bigger CPU count deployment. But we still get a really good improvement even on low scale deployments, which is a good result.
And this is this is not the final Leyden. This is still pre-main is not
it's
finished.
Still being tuned. Yeah, we've still got work to go to get this as much as possible out of this. So this is a work in progress still. Yeah,
and not all the classes are initialized when and store initialized. So there's still when you load them, there's still work to do on most classes to make it ready to be used. So this is the pre-main. By the way, it's called pre-main because it's things that happen before the main in Java. So this pre-main is still not finished. This is for JDK 27. So we still have time to improve. So it's going to be even better.
Okay, let's move on then, Maria, to the next one.
So this is individual request timing. This is graphs that show. Note that the x-axis is the not time is the number of requests. So we see for each request how long does it take to finish and answer to the client. So here we can see on the left side we have the first 100 requests, and on the right side we have from 100 requests to 500. We have separated them because as you can see, after 50 requests everything goes down. So it did
so
make
we've
sense.
Adjusted the scale, we've rescaled it, so you can see the detail in that very low bit. Yeah.
So you can see that pre-main JDK just runs at the beginning. It takes some time because it's loading metadata, it's compiling, it has to do all this startup and warm-up process, and then it finishes. And after 50 requests, it's just maintenance. It's not maintenance, but it's the difference is too big. We can say that this is already warmed up. Then
just to clarify, the pre-main is the red line. So the pre-main has got the least disturbance of the request times go up a bit in the first 50 requests. And then if you look at the sort of requests from 100 onwards, it's bumping along the bottom, and the interruption from the VM is almost nothing. It's sort of random. So basically after the first 50 requests, pre-main is just serving at peak capacity. But during those first 50 requests, it's got to do some work like class initializations mostly, a little bit of compilation and so on, because not everything is in the cache, but most things are in the cache. So go on, Maria. And then the green line was the AOT for JDK 26, and the blue and yellow are the non-AOT cases.
So you can see that pre-main has much better time response with AOT than JDK 26 with AOT, but that's to expect because we already have compiled code. And if we go to the two cores, it seems like response times are better, but that's kind of tricky because that's not entirely what is happening here. Because the thing is that some of the profiling and compilation with 4 cores is done earlier because we have more threads doing compiling at the same time in parallel. So that's why the numbers may be a bit higher on the 4 core than the 2 core. But that means that we reach peak performance earlier because we are doing part of the work early.
Yeah, and in fact, you can see that on the graph on the left. When we get to the point where most of the initial work has been done, you can see the green on both the 4 and the 2 core mean that the pre-main, the JDK 26 case, we've got method profiles in the cache, and so we start compiling code a lot earlier because you don't get method profiles straight away. It takes a while for the method profiles to actually arrive in a normal run because you have to run in the interpreter. With JDK 26, we've got method profiles in the cache, so the compilation starts early. So I'd request 100 on the right there. What you can see is that while we're still bumping along with jitter in the blue and yellow cases where there's VM activity going on, we haven't really started doing most of the compilation. There's a bit of compilation start on the yellow, but we're actually doing a lot of compilation. That's why the requests are getting interrupted and slowing down for the green, for the JDK 26 case. And that's because right from very early on, we have a load of method profiles in the cache. We can start compiling code straight away. And we currently compile code greedily. We start actually compiling. So we get this compile spike quite early. If you look with 2 cores, the compile spike is starting, instead of around 200 and starting to go up, it starts to go up around 500. So what that's showing is that because there's less cores around, the compilers are taking longer to finish the compiles, so we don't get into the process of compiling quite so quickly. So the compile spike, the influence of the compiling happens later on. It's delayed and it's spread out over time. So where this hump here up to 900 goes up, it comes down quicker with 4 cores than it will with 2 cores. We're sort of getting the interruption done earlier and we're stabilizing earlier, but we pay more penalty with 4 cores. So this is, again, one of the things that we need to trade off, evening out the work by making sure that the compiles we do are done in as spread out as much as possible. But of course, once we get the compiled code in with a well-trained application like the one we've got here, we don't have any compilation to do. So we start bumping along the bottom at full peak capacity, almost from request 50 when all the basic work has been done. I was one other thing to notice. That's 50. This is the point of 50 requests. Most of the initialization, the real bulk of the initialization, initializing classes, pulling stuff into the cache, has already been done. There's a sort of much smaller amount of that going on. But the times here for these things have to take the number of requests multiplied by the average time. So those 50 requests for the AOT case, they happen with requests that are getting dispatched in about 1 millisecond or half a millisecond. The 50 requests happening in the green case, the pre-main AOT case, each request is taking a couple of milliseconds on average, 1 millisecond or 1 a bit on average. So the time to get to the point where all the work is done is different, even though it happens roughly the same point in the program execution. It happens at the same point because the program does much the same stuff every time, but doing it in a VM that's got AOT cache and compiled code happens quicker than doing it in a VM that has AOT cache and no compile code, and it happens slower in a VM that doesn't have any caching at all. And that's what we're seeing here. Although things happen at the same point after so many requests, it's actually happening a much earlier time for the AOT cases. Okay, Maria, next slide maybe.
Yeah, so this is histograms for response times for each case.
For the
So here we remove the 2 cores. We are going to show it on a later slide. So this is the four cores: JDK 26, AOT, JDK pre-main normal, pre-main AOT, and we start on 200. So this is after on the previous slide. We start here on 100. This is 200. So we are starting around here, and as you can see, well. On JDK 26, we are still compiling things. And at some point, we kind of slow down on 7,000, and that's fine. And then with AOT, we have many more compilations happening that delay. I mean, the delay is just 0.1 milliseconds, 15 milliseconds. It's something negligible, very small. You wouldn't really notice this on a production server unless you are running very, very high loads and you are running at your top capacity almost. But there's a lot of compilation, and this compilation does not happen here, as we have said, because here we already have the profiling, and this is going to happen much later on the JDK 26 without AOT. So maybe this is calming down, and at 20,000 requests, it starts compiling and recompiling with optimizations. So the thing is that we get to a lower or a more optimized code faster with AOT because we already have the profiling. And maybe you want to talk about pre-main?
Yeah, with pre-main, I mean, the pre-main stabilizes, it's sort of bumping on the bottom about 7,000, a bit like this one is, it's slightly later. But with the compile code already in place, we get essentially random noise right from 200 requests. And in fact, if you go back, it starts even earlier. So this has definitely got to the point where it's running at peak performance way earlier than if you didn't have the AOT. The Leyden prototype really gives us an enormous benefit. This one, it's pretty much stable here, apart from that little bump, which is just a bit random. So we're talking about having about 6,000 versus about 7,500. But with the compile code and the cache, we get to peak performance really quickly. One of the things it's worth mentioning also, we actually train this application by sending 30,000 requests to the server and then dumping a cache. So the training run made sure we'd got all of the work that's going to be done, pretty much all done by the time we saved the cache, because look, we're up to about 10,000 and this thing is already really stable. Even it's stable without an AOT, it's stable by about 10,000. So we've made sure we've got a really good training run here. Now, one of the consequences of not having a good training run is you get less code and less profile information and less classes in your cache. So you'd have, with an application that wasn't run for quite so long, trained quite so well, you'd see more of this interference for longer. If you can manage to get something that really replicates the runtime conditions, you'll get no interference almost from the start. You basically got all the assets you need in the cache and the thing runs really fast. So that's why I was saying before, the training run is really critical. The more you can run in a realistic situation long enough to get compiled code, to get all the linkage there, all the method profiling, the better off you are. Even if something has to decompile, because you've got good profiling, you'll recompile really quickly and you'll get back to compile code quicker. So even in situations where the code doesn't quite match what happens at runtime because of some variation, you'll still get really, really good peak performance with very little interruption from the VM having to do things to repair the situation.
Yeah,
and we can look at the same for two cores. We'll move on to that, Maria. It's much the same sort of story.
Yeah, it's much the same. And the main difference between these two is just that this needs to compile. This is already compiled.
Yeah,
that's the main difference. And with two cores, the history is very similar. We just don't have such a high compilation bump here, just because we don't have as many threads, because it detects it's only two cores. We don't have as many threads compiling code at the same time in parallel. So it gets a bit more spread over time. And I think there's not much to discuss about 2 cores.
Yeah, I mean, with pre-main, what you can see is that because we've got 2 cores, with 4 cores, when the compiler was cycle stealing, we didn't really notice that much because the server's running at about 2/3 full capacity. So there's a bit of spare CPU to grab. But with 2 cores, because the compiler has to do all that same work, it starts to have a little bit of effect. So rather than bumping along the bottom with no influence, in the early few hundreds, we see that the compiler's stealing cycles to do work, or the loading and class initialization that's left to do a little bit of work that's still needed, even with a well-trained app, it's a bit more noticeable. So depending on how tight your deployment is, you may still see some jitter, some influence from the VM doing stuff, but it's still very low. We're talking about below 0.1 of a millisecond here. So the interference is very, very small. We've got all the real interference in the first 50 results requests all out of the way, and you're very quickly into the point where you're at peak running with AOT code. Okay.
How to use it? Well, of course, you need to run a training run with this argument in your Java line code. And you can also have a training and an assembly run in separated steps. This is just training collects the data, assembling builds the cache. Or you can have them both together. It depends on how you run your training. Maybe you want to run the assembly wherever you are running your training, or maybe you want it separated. And once you have the cache, you just add it with another Java argument, and then it runs. And if you are going to test this, please share your results. And even if the results are not what you expect or what you want, those are the most interesting results, because if it is not behaving as it should or as you expect, then maybe there is something we can fix there, or we can improve. And that's the real interesting stuff. We want to know about the good results, because that's very reassuring. Oh, we are doing a good job. But we also want to know if something is not working as you expect or as you want it to work, because that's where the work may be done to improve this. So please, if you test this, and please test this, share your results with us. Andrew, you want to talk about the different models?
Yeah,
maybe?
I mean, obviously, you'll get the basic capability without the compiled code when JDK26 is fully released. So that's actually just happening now. I think it's actually out the door, or it's very close. So you can test JDK26. If you want to test the pre-main prototype, we have a Leyden pre-release image that you can actually get from the Leyden project. Go to the Leyden project on the OpenJDK site, and you'll find instructions on how to get hold of one. We may well do another early access release with the latest capabilities, although obviously we're hoping to get something out in JDK 27 timescale. So there is a possibility of trying out the pre-main stuff. When it comes to training, there are different approaches to training. So with Quarkus, one of the things we've built in, if your Quarkus application has an integration test, then there's mechanism in the Quarkus POM and the Maven support with the Quarkus Maven plugin to allow you to run your integration test and get it to exercise your code and to generate an AOT cache. Now, that's not fantastic, because an integration test won't necessarily exercise very much of your code. It won't necessarily run for very long, but it is a simple way of getting an AOT cache. So there's a configuration option in the Maven plugin that allows you to use your integration test as a way of generating a cache. If you want a better training run, there's 2 other approaches that you could consider. If you can run your deployment in a sandbox and feed it synthetic requests, well, then that will be a really good way of getting a much more reliable training run that gives you a cache that's going to have most of what you need. Although, of course, it's based on synthetic data, it's maybe not going to be realistic. But what we used was we ran our server with some synthetic data. And then, of course, our benchmark, we also ran with the same synthetic data, which is why we had a very well-trained cache. The gold standard is that you actually use what's called a canary deployment. So you may deploy one or multiple copies of your server, and one of the copies of the server, or it's the only one if you've got it, is configured to do a training run, to say, give it an AOT cache output target, and it will run. And then when you stop that server after it's run for however long, you'll pay the penalty of having some monitoring going on while it's running. At the point where you kill it, it will fork another JVM that will actually generate a cache. And that's it, your server's exited and you've got a cache. And then you can feed that cache back into your next server run. So a canary deployment is one of the sort of best ways of getting a realistic run, because you're using real live production, real live user input to train. Of course, it means that while you're training, that one server you got deployed is going to run slightly slower. So you have to take the hit. This is the approach that's been used by some of the big commercial companies who've actually already adopted JDK 26. And it is a really, really good way to get a really big performance boost. There's some very big organizations. I mean, Netflix announced that they were using JDK 26 in production with Leyden to get using this sort of deployment model. There are some other big companies doing a similar sort of thing. So depending on what you've got as your build pipeline and your deployment pipeline, you may or may not be able to use one of these models. But this is really critical. The closer your training run resembles your production run, the more stuff you'll have that's actually what you need in your cache, and the more bases you'll have covered.
Yeah, if you are going to use integration test, for example, be very careful not to load too many test classes, utility test classes for your testing, because those test classes are going to end up in the cache, and then they will get load at startup, and also they will shadow maybe important classes that will not be trained and cached. So or if you are not using canary deployments, but you're using some sandbox, and that sandbox is using requests that are not a copy of the requests, that they are not duplicating the request a normal server does, then that's a problem also, because you are not replicating what your users do. Do we go for the demo, or do we go for the questions? Because we are already on time.
Yeah, we're really a bit out of time for the demo. Maybe we can postpone that. Let's answer a few questions first, because if people want to hang on, we can do the demo. This is a really good question. How do you debug performance issues? Well, many of the performance issues are just the performance issues you'd have anyway. The tools that you use for monitoring the actual deployment are the same, because by the time you've got through startup and warm up, you've got all the code in your cache, in your system, all the classes in your system that you would normally have, and it's just normal running. What Leyden is doing is just optimizing getting to that peak running. It doesn't really much change what's going on when you're actually at peak performance. So if your peak performance has gone down a bit, then Leyden has caused a few regressions, but there shouldn't be many of those. We're working on that. There are one or two cases we do know that sometimes the code that you end up with isn't quite as fast as the normal peak performance code. One of the things we sometimes have to do is, when we compile code in advance, put in class initialization barriers where we check whether a class is initialized, and first time round we dive out, initialize the class and run it, because we can't guarantee the order in which classes are loaded. So sometimes the AOT code has a little bit more extra work that it needs to do. Normally we try and replace that with fully optimized code later on, but it doesn't always work. So there are occasional regressions, but mostly you should end up with the same dynamically generated, same code for your run as you get from dynamically generating, with all the same classes loaded, and your performance should match what you get normally. So if there's a performance issue at peak running, it's because you've got the performance issue. The other interesting half of that question is, how do you detect problems in getting better performance, optimized warm up and optimized startup? How do you know whether Leyden is really giving you much of a gain? And this is one of the things that the tool that we're going to demo actually helps with. You can look at the cache, and Maria's developed a tool which allows you to have some idea of what's in the cache. The obvious answer is, well, if it starts up quicker, or if it reaches peak performance quicker, and you can measure that by seeing how fast is it answering requests and where does it get to the point where it's answering at full pelt. If it's quicker, you're gaining and you've won. And if it's not quicker, you're not gaining. And if you try different training regimes, and some training regimes give you better results because you get to start up quicker, the port opens quicker, or you get to warm up quicker because your request rate is now at full pelt after 20 seconds rather than 30 seconds, well, then you know you're winning. So if you can measure the performance rate in some way, you can measure when you enter the application in some way, possibly with a log statement or something, or with monitoring like using JFR or something. Well, in that case, that will tell you what gain Leyden is giving you. But what you really want to know is what's in the cache. How does what's in the cache actually tell you that you've got stuff that's valuable or stuff that's not valuable? So Maria's tool is a sort of browser for the cache, which tells you how it was built, what actually is in it, how many things there are in it, what gets used at runtime and what doesn't get used at runtime in your production run. And that's really the best tool. So Maria can maybe talk about that.
Yeah, so this tool is open source available. And the idea is that it takes the training logs, production logs, and AOT map file, which you can generate using those arguments in Java. And it analyzes them and it tells you a bit how well or bad your cache is. So I'm going to load an AOT cache. I'm on the right folder? Yes. From pre-main using the Quarkus with the custom-defined class loader, the custom-defined
the normal packaging model, which means
yeah.
It's a bit like having a badly trained app because only a subset of the code is able to be AOT cached. So if we use the normal case, the normal jar, we can treat that as being like a not very well trained app. And if we use the Uber jar, we can treat that as being like a well-trained app. And we'll see the difference in what's in the cache between one and the other will tell us some idea of how much value the cache is giving us for running the same application.
Do I have... I don't have the...
Well, if we had the right files, we could do this. Also,
no,
it's running slow because you're presenting and you're running on the machine at the same time, Maria. So this is going to be fighting for cycles. This is the problem with demos. When you try and do something live while you're running a screen share,
I have it. I was looking for this, and I'm going to run it in background, so it's I can load other things at the same time. So this is using pre-main, and this is using. I'm loading the same one.
No, you've got pre-main, but you should have the normal jar. Oh, you are. That's the normal jar, and you want the Uber jar, yeah.
No, I don't want the Uber jar. I want to compare pre-main and JDK 26.
No. Well, you could do, but it's probably better to compare pre-main Uber jar and pre-main normal jar.
Do I have?
You do have them, yeah.
I've done this so many times. Well, let's compare whatever. Uber jar training AOT map. I have this one too.
Well, meanwhile, while you do that, Maria, I'll answer the next question. Yeah, at the moment, if you have an agent in your on your command line, you can't use the AOT cache at the moment. We know this is a really big deal for people. Let me explain why. So imagine you've got a class in the class path and the agent transforms it. And we base what we do to generate our cache on that version of the class with that bytecode that's been transformed by an agent. And then later on, we rerun and the agent's there and it transforms it in a different way. Well, we'll be using, say it has a different policy for how it wants to transform. We'll be using code that was transformed when we built the cache using one policy, and we might be mixing it with code that was transformed live in the production run that's transformed using a different policy. We don't have any hard guarantees that transformations that happen when we're doing our training run will be done exactly the same way as they're done when we use our production run. This is the same rationale for why we can't support custom class loaders until we've got some guarantees that we have known class loaders that are going to provide the same bytecode in exactly the same format for a given class. Anything we save during the training run might be served up differently during the production run, and we can't mix and match stuff that's taken from the assembly time and stuff that's taken from the production time. So until we get some way of controlling and constraining what agents do or what custom class loaders do, we have to rule them out of the mix at the moment, and we won't be able to AOT cache anything that's touched by an agent or touched by a custom class loader. Now, we're hoping to weaken these restrictions and either for specific cases we know are safe, or to provide a model for how you can make guarantees and be sure that you're using technology that's going to work. If we get this wrong, it's not that it just might not, it might not sort of give exactly the right results. It could crash your application, or it could even crash the VM. So we're being very cautious at the moment in what we allow, and we're ruling out cases that add these unknowns into the equation. We know this is an issue for people, particularly something like Dynatrace, and we really want to be able to support that. So we're working towards that. But again, that will be a priority for some of the later releases. It's probably not going to be something we get in before 29 at the earliest for some special cases, maybe even to 31, 2, 3, before we get to the point where we've actually got this sort of thing supported and really working in a bulletproof way. So that's the situation at the moment. Right, Maria, how are we going?
We have the pre-main normal, and I'm going to load the uberjar pre-main.
Okay. So what stats can we see in the pre-main normal cache? What can you tell us about that cache?
Take some time because I'm doing too many things at the same time.
Yeah, including presenting.
So I forgot to put it in background. Okay, so this is the normal one. This is the one that have the custom dedicated custom loader, class loader, and it means not all the source code is available for Leyden, because part is hidden, not hidden, is loaded with the custom loader, so it's not considered by
cacheable
at this point. Yes, so you can see that only 86% of classes are cached. This is very low. Well, very low, depends what you do, but usually you should have something closer to 100%. And then for Lambda methods, this is even worse, because most of the Lambda methods on our source code comes from Quarkus, which means they are loaded using this custom class loader, which means they are not considered for caching.
Yeah, and pre-linking lambdas and getting rid of the need to identify, run a bootstrap method to get a method handle is one of the big optimizations that arrived with JDK 25. Most of the benefit of having pre-linking is that method handles are already pre-computed. You don't have to work out where's the target method and run Java code to do it. So losing out on having lambdas means you do a lot more work at runtime. So it's a really big deal not having lambdas cached.
I'm trying to close stuff, but this is slow. Usually this is not this slow loading stuff.
Have we got compiled method information there? We have, haven't we?
Yes. We have, this is pre-main, so we have a big cache of code, and we have compiled methods here. You can see that the percentage of methods that are compiled high on a high tier and high optimization is not that big. Most of them are low.
Those are C1 methods. Yeah.
It depends on how you train it and the kind of stuff you were able to store.
But in this case, many of the methods you want in the actual application, which are the ones you really want to be optimized, because they're the ones to be running during service, aren't actually compiled at all. So there's even though this is the fully pre-main AOT implementation, it's still going to end up doing quite a lot of compilation, because only some of the methods are actually run during the training run in a way where they could be AOT cached. So this would be the same sort of thing if you had a fairly minimal training run. You'd find that you've got a few methods compiled, which still is beneficial, but not as many as if you had a really realistic training run. And we should get those figures fairly soon on the left-hand side.
Yeah, we are still on less than 500,000, and we have to get to this more than this number because it's the Uber jar, so it is able to cache more because it doesn't have the dedicated class loader.
Yeah. So that's why it's taking long to load, because there's a lot more to load as well.
Also, there are some elements here on the cache that are bigger, so it's slower to process. So we are getting there.
Mm-hmm.
Yeah, we are there. So now we load some training logs. We only have one training log? That's suspicious. No, 2 training logs. That makes sense. And the production log, that's important to see which ones...
which one actually got used, yeah.
What was used during...
So the training log tells us what was actually put into the cache and what was run during the training run. The production log tells us what's been used, what's been consumed from the cache. So all the log information that's generated tells us about actually how effective the cache has been.
Oh, I don't have the UberJar production log because this is not the production log.
Oh, okay. But we do have information about what went into the cache, don't we? We have cache statistics.
Yes. So we know that there are like 3,000 more classes in the cache.
And what's that as a percentage? Is it nearly 100?
No, we don't have the percentage because we don't have the production logs.
Yeah.
Why we don't have the production logs, I don't know. And I don't know why we don't have the code cache data either, because it's on the production log, the code cache data.
Ah, right. Okay.
Oh,
well, yeah. Okay. So what we would find would be that there'd be way more compiled code. There's like 4 or 5 times as many compiled methods in the Uber jar case than there are in the normal jar. And that means that essentially almost all the code you need to run this application is actually already available. It's not just application code, it's also JDK runtime code. JDK methods are also compiled in there as well. So
you can also
see quicker, and when you call out from the application into the JDK runtime to do things, that also runs quicker.
The profiling for methods are, we also have more information, which means we were able to run them, profile them, and possibly compile them.
Can we also have a look at how many Java-Lang class objects are in there? That's another interesting measure, because that's a measure of how much you've actually pre-initialized classes. So we can look at the objects that are in the code cache heap and look for objects of type Java-Lang class. We should see how many there are.
So here we have only 3,000 Java-Lang classes, and on the pre-main UberJar with no custom class loader, we have almost 15,000.
So what that means is we've already pre-initialized that class. We don't have to do the class initialization. So that's another point where when we're running with the well-trained application, we bypass an enormous amount of work for having to initialize classes. Whereas and create the Java-Lang class object in the heap, it's already there with all the static field data already installed there.
And we can see that we have warnings. That means how many classes throw some or errors that were thrown during creation of the cache or loading of the cache. That's useful when you see something that is weird. You can also check the warnings and see what happened. For example, maybe some class failed some validation, so it was not stored in the cache because it was not considered safe to be stored on the cache, things like that. What else can we show? We can see if how many classes were loaded during production that were not cached. 187, and I cannot do the same here because I don't have
the production log.
But you can see that most of these are Hibernate classes. Why were they rejected from storing the cache? I don't know, but that's interesting to explore. It looks like if we weren't using Hibernate, most of our classes will be cached for some reason. That's probably because this is the ones that were behind the custom class loader in this case. But
Yeah.
I mean, if you are exploring why your cache is not 100%, what's happening, you can try to take a look at this and say, oh, this is the class that are not here. Why are they not cached? And then you can explore it.
And in fact,
we are really over time.
Yeah, we are, but one of the things that we're looking to with the tools is find situations where something's not loaded or where a warning occurs, and try and work backwards and see what that warning means and what it says about the application. So if you use this tool and you find things that aren't loaded, or you find things that you get a warning saying we can't add this to the cache, this is the sort of thing that we could look at, and if we can reproduce your application, you can give us a way of running it. Or running as something that manifests the problem, we can diagnose what's going on and try and tell you why it is that this application fails to be able to cache something. The more we get experience of this, the more we're able to say, oh, that's easy, we know about that case, or that's straightforward because it's this type of thing that's happening. But we're still working through using this tool and understanding all the things that might go wrong. So we'd really like people's input and help in trying to diagnose these things. And we're very happy to get online with you and talk it through with you, because your experience is going to be of real value to us, and we can help it to make the tools better for everybody.
Also, this is Leyden is like not early stage of development, but we are very early or mid development. So if you try now with your application Leyden and you find that it is not giving all the juice that can give to your application for whatever reason, this is the moment to ask us and say, hey, my application is not working fine with Leyden. Why is this? Is this something that is planned to be fixed, or some enhancement that is not yet published or whatever? Or is this something that you haven't think about or haven't realized yet, that this use case specifically Leyden behaves not as it should, or it could behave better? This is the moment to tell us, so we can think about this. We change the architecture, we change the things we are going to do, and then Leyden can adjust better to your use case. If you wait for JDK 29, JDK 30, when this is maybe more mature, it will be harder to incorporate your use case. So this is the moment to test Leyden and see if this is already working for you. And if it's already working for you, just please use it. And if it's not, then collaborate with us. This is open source. Everybody can join and collaborate with us and see why this is working or is not working.
Yeah, and in particular, I mean, JDK 29, that is the next long-term support release, is clearly the thing that we'd like to get stuff really working and really tuned and really answering everybody's needs. So the more you can get early feedback to us now, the better JDK 29 will be for you to do not just development, exercise this in development, but to actually get real live deployments out there that you can support for multiple years on a long-term support release.
No more questions, I guess. Hi, Taco.
No. Hi, no. There are no more questions, so I think that's the end, right?
Right. Well, thank you very much.
Thank you very much, you too. Thank you very much for this talk. Very interesting. I've learned a lot. Even for me, that I'm on the team, I learned a lot. So thank you very much. And well, have a nice day, everybody who is still here.
Bye.
Bye.